This section is on inverse functions. So in this section, we will identify one-to-one functions, define the horizontal line test, and verify inverse functions. Modern cryptography intersects the disciplines of math, computer science, and engineering. Applications of cryptography include ATM cards, computer passwords, and electronic commerce. Cryptography is the science of making and breaking code. Until modern times, cryptography referred almost exclusively to encryption, which is the process of converting ordinary information, plain text, into unintelligible gibberish, ciphertext. Decryption is the reverse. In other words, moving from the unintelligible ciphertext back to plain text. For example, would you be able to decode the following message if I gave you a clue? This is the message: ES space UIPNBT space, and so on. So these are words. It is unintelligible at this point. It's definitely not the English language, but the words that are the words convert to an English word. If I gave you the clue, and my clue to you, or my key, as they call it, if I gave you a key to unlock the message, it would be shift every letter once in the alphabet. I'm not going to tell you how, but that's just my clue. So if you want to try it, I would say pause the video now. See if you can figure out what I mean by shift every letter once in the alphabet, and you will figure out what this says. So pause now and figure it out and then play. Okay, so some of you may have figured out that this says, and I agree, Dr. Thomas is the greatest. So to get that message, you had to shift where? Left or right? E, A, B, C, D, E. D comes before E. R comes before S. T comes before U. So you had to shift to the left to get the message or decode the message. So by the end of this lesson, you'll be able to decode the following message. Notice you have numbers. So you're using your knowledge of inverses, you're going to be able to decode what that message is. All right, one-to-one function. A function f of x is a one-to-one function if x values do not share the same y values. A one-to-one function will have different x values and different y values. Are the functions one-to-one? Below. Well, you can tell if the functions are one-to-one by something called the horizontal line test. Now, you've heard of a test before. What test did we discuss earlier that you know about? Vertical line test. The vertical line test told us what? The vertical line test told us whether we have a function or not. So, for example, on the left here, does it pass the vertical line test? It does pass the vertical line test. Therefore, we do know that this is a function. Right? Check. It is a function because it passes the vertical line test. Now, question is it a one-to-one function? Yes, it also passes the horizontal line test based off, you see, there's a horizontal line. So again, if it only touches the graph once, it passes. the vertical line test and the horizontal line test, right? So it only if you drew a vertical line, it will only touch that graph once, therefore it is a function. And by that maroon horizontal line, you can see that it passes the horizontal line test as well. So therefore it is a one-to-one function. If it passes the horizontal line test, it is a one-to-one function. Let's look over here on the right. Question, is it a function? Yes, you can look at the y-axis to see that it passes the vertical line test, but does it pass the horizontal line test? No, right? No, therefore it is not one to one. No, not one to one. Okay. Let's go on to this next page. Why are one-to-one functions important? One-to-one functions have inverse functions, and then we're going to go over a real-world application of using inverse functions, which is to decode a message, right? Using cryptography. So just showing you that inverse functions can be used in real-world applications. So that's why we want to know if a function is one-to-one. If it is one-to-one, it has an inverse function. Let's start with the basics. Let's look at this point 4, 7. Its inverse point is 7, 4. And let's look at this point -5, 3. Its inverse point is 3, -5. What happened? As you can see, the x and y switched. You can determine the inverse point by switching the x and y. 4, 7 becomes 7, 4. -5, 3 becomes 3, -5. Inverse functions are symmetric about the line y equals x. So this is the line y equals x right here, right here. Down here. So the line y equals x, remember, that is called identity function. So if you recall your parent functions, those were one of the functions I asked you to memorize. Yes, identity function is linear. But notice that if we folded this blue side over here and this red side over here, right? We folded it across that line y equals x, then it will basically be mirror images of each other. So that's all it's saying. That's one way you can determine if you have functions that are inverses of each other. Let's say the function in blue, there's a function in blue and there's a function in red. They are two different functions. But if you fold it across the line y equals x, they are symmetric. Therefore, that's one way you can tell graphically if two functions are inverses of each other. So let's practice graphing so you can see two functions that are inverses of each other. Let's look at f of x equals x squared plus 1 and the square root of x minus 1. But let's look at f of x equals x squared plus 1 when the x's are greater than or equal to 0. All right, greater than or equal to 0. All right, so let's go with that. Graph f of x equals x squared plus 1. But the restriction is that the x's are greater than or equal to 0. So when we draw our t-table here, since the restriction is the x being greater than or equal to 0, we're going to start with 0. And we can plug in 1 and 2 and 3, for example. So when we plug that into x squared plus 1, 0 squared plus 1, we get 1. 1 squared plus 1, we get 2. 2 squared plus 1, we get 5. 3 squared plus 1, we get 10. So let's plot those points. We have 0, 1, 1, 2, 2, 5. All right, y'all see it right there. Let's just do that part. And then let's graph its inverse function. So this is the notation for inverse function. It's telling us that it is the inverse of the one we just did. So let's graph the inverse function, square root of x minus 1. Now, as far as the square root function is concerned, what is the domain? How can you determine the domain? So if you can recall, when you ever have a square root, you would set what's under the radical. So let's put domain. You would set what's under the radical to greater than or equal to 0. So the x's in this case must be greater than or equal to 1. So there is a restriction. The x's have to be greater than or equal to 1. So 1, for example, will work. That's a nice number to plug in. You get 0. What about 2? 2 is looking good. 2 minus 1, square root of 1, which is 1. I think the number 5 would be good because the square root of 5 minus 1 is the square root of 4, which is 2, for example. So let's plot those points. 1, 0, 2, 1, and 5, 2. So notice you've got that square root function going this direction. All right, so that's showing you that these two functions here are symmetric. Again, about the line y equals x. Notice if we fold it across this dotted line here, you have mirror images of each other. All right, let's talk about the horizontal line. Let's go over some examples just to make sure you got it. First of all, does this graph pass the vertical line test? Yes, it does. So it is definitely a function, right? But is it 1 to 1? I'm going to use a little shortcut way of writing 1 to 1. No, it hits that graph more than once horizontally. All right, what about this? Is this a function over here? Yes. Is it 1 to 1 though? Yes. All right, because it only hits that graph once if you do a horizontal line. All right, let's move on to the next page. Do the following graphs pass the vertical horizontal line test? So we're being redundant here, but it says it passes both the vertical and horizontal line test. And so it is the graph of a function that has an inverse, which is also a function. The next one, look at this. What does this look like? Absolute value function. It passes the vertical line test, but not the horizontal. So vertical line test, yes. Horizontal, no. It's hitting it in 2 spots, not only 1. So it is the graph of a function, but it does not have an inverse that's a function. This one here, it passes the vertical line test, but not the horizontal line test. Therefore, it is the graph of a function, but this function does not have an inverse, also a function. And this one does not even pass the vertical line test, right? Therefore, there's no need to apply the horizontal line test. All right, does this graph pass the vertical line test? Yes, it does. However, does it pass the horizontal line test? So function, yes. Right? Function, we can agree on. What about 1, 2, 1? No. Is this circle or oval a function? No. So there's no need to apply the horizontal line test because it tells us if it's not even a function, then we don't really care about it's not gonna, we're not gonna be able to get applications out of that one. All right, now let's look at this graph right here. Consider the ordered pairs -2, -6, -1, 1, 0, 2, 1, 3, and 2, 10. F of x equals x cubed plus 2. So notice, which one do you think that is? Do you think that's the graph in blue here? Or is it the graph in red? So if you know your parent functions, you know that that cubic function looks like the one in blue. And notice that it's plus 2. So that means there's a vertical shift up 2 units. And notice it is up 2 units here. So this must be the one in blue, right? And this one is the one, the cube root one is the one in red. It says switching the domain and range. So if we're switching the domain and range, notice -2, -6 becomes -6, -2. -1, 1 becomes 1, -1. 0, 2 becomes 2, 0, and so on. So your x and y switch. So if you have two graphs that are inverse functions of each other, then you know that the points would be flipped. All right, that's how you know. So for this function, y equals 2x plus 1 on the right here. If I ask you to graph the inverse function, then you shouldn't have a problem. All you have to do is identify points on this y equals 2x plus 1 graph, like 1, 3, like 0, 1. These are not the only ones, but these are the ones that are highlighted in red. So let's just go with it. 0, 1, and this one is -2, -3. So our inverse function will have the points, what? 3, 1, 1, 0, and -3, -2, for example. So we plotted that, we get 3, 1 here, 1, 0, -3, -2. Get that? That is not a very good line. I'm doing this by hand. All right, so notice that those two functions are symmetric about the line y equals x. This concludes the video on the horizontal line test and how you can determine whether we have an inverse function based on that horizontal line test. We know that points are switched for inverse functions, and we also know that two inverse functions are symmetric about the line y equals x.